Okay. Okay. So thank you very much for the presentation, and I'm really honored to be able to give a talk here. In fact, I'm somehow surprised when I got invited because I'm not working on algebraic topology or geometry. Actually, it's about Lie groups and the representation theory. So, by the way, I think the internet connection in the campus is not so good. So, in case that my connection dropped, please inform me on WeChat or whatever. Okay, so anyway, so I made some slides. Actually, it's for another conference, so the slides are maybe a little bit technical and it's too long anyway. But in case of need, you can find the slides on my webpage. So let me get started. So there are two keywords in the topic. The first is localization, and the second is branching laws. So let me start by explaining these two concepts. All right. So no, wait. I have to set something. Sorry. Okay. All right. This is not so good. Okay. So the first question is, what is localization? So as in the previous talks, all the groups and varieties are algebraic over C, and we say a variety X is a G variety if Gx on the right, algebraically. Everything is algebraic, almost algebraic in my talk. So let G be a affine algebraic group and X be a smooth G variety. Then Gx on X, so you can take the vector fields generated by the infinitesimal action. So get a homomorphism of algebras from the universal enveloping algebra UG to what? To the algebra of algebraic differential operators dx. So here dx is the okay. There are two dx. The curly dx is the shift of algebraic differential operators, and the Roman dx is global sections. So localization is just tensor product using this homomorphism. So it maps a G module to a D module over X using J. So so far this is a really simple definition. And here, of course, G mod means the abelian category of left G modules, and dx mod means a category of D modules over X. Here, D modules are always quasi-coherent over the structural shift. So why are we interested in this functor? For me, at least for this talk, it's interesting because it's related to co-invariance. So there's a relatively easy fact. Let X be a homogeneous space, G mod H, and let Ix be the inclusion of the base point. So if you localize the G module and then take its fiber at X, here the fiber is taken in the sense of just of quasi-coherent shifts. Then it's not too hard to show that you will get the H co-invariance. And if you take its linear dual, then you get the space of or H invariant linear functionals on V. But you can also view X just as a homogeneous space and let the base points move in a space. Then you can also vary base point X and its stabilizer H. So the point is, in this way, localization just organizes all these spaces of co-invariance into some geometric object over X. So any questions so far? Okay, then let's go ahead. So this is about localization, and some first examples. For example, if you take X to be a flag variety and allow some twists on your D modules, then we get the famous Beilinson-Bernstein localization. And another case is to take G to be two copies of group H, and here I think we should suppose H to be a reductive group. Anyway, so, and we take X to be H itself. So the action is just left and right translations. So recently, Bensby and Ganev studied this functor, and they also studied the specialization of the D module at infinity. And use this, they get some information about asymptotics of matrix coefficients of admissible representations. It's something about D group representations. It's something about analysis. I won't go into details of this. But anyway, this shows it is of some use in representation theory. And in the second case, X is actually affine. So for affine case, we just forget about the shifts and work with global sections, dx. And secondly, even for affine X, one can show that localization functor is usually non-exact. In fact, in many cases, you can write down a G module and with non-trivial tau functors. So we should also look at the derived functors of this localization. This is what I mean by higher localization. Higher means higher derived functors, but this is more complicated than it seems. We will see. Okay, and the second keyword is branching law. So in a classical setting, we consider two groups H and G. So you can take finite groups or compact Lie groups. So for a reasonable representation V of G and W of H, the branching law studies the decomposition of V over H. So in other words, we study the home spaces of between a V and a W, but taken over H. This is about how a V branches over H. And often we consider, in Langland's program, we don't really work with competitive groups. We consider either periodic groups or real Lie groups, which are not always, which are often non-compact. So there are many versions to formulate the problem for Lie groups. So the simplest version is to work with the algebra. So V is a module over G, the algebra of G, and W is over the algebra of H. We study the home space, but now everything is over the algebras. So this is algebraically simple, but for Lie groups, representations is often more useful to consider GK modules. I will review GK modules later on. It's what related to a representation of Lie groups. Okay. So okay, let's move on. I have many slides. So now let G be a connected reductive group and take a subgroup K. So in representation theory, as I said, we are interested in GK module. That's a G module with compatible and algebraic KH. And there's an interesting subcategory of modules called Harish-Chandra GK modules. So I won't say too much about compatibility here. Anyway, you can imagine that there's some condition of compatibility, and I will review it later on. But let's explain what is a Harish-Chandra G module. We say V is a Harish-Chandra GK module if first it is finitely generated over G, and secondly it is locally GG finite, where GG is the center of the enveloping algebra. Locally GG finite means every vector in V is contained in some finite dimensional GG submodule. For experts of in the group representation theory, people always phrase this condition in another way called admissibility. So this is actually equivalent to the definition I wrote down. But I won't use this notion because the version above it fits better with the geometric picture. So the Harish-Chandra GK modules are what really appeared in representation theory of Lie groups. For example, one can show that every irreducible GK module is Harish-Chandra. Okay. So what about? So I'm going to talk about regular D modules. So how does this arise? For example, let's take the work of Benson-Lee and Garnett, for example. So they work with the group case. So they consider two copies of H. H is a connected reductive group, and the X is a homogeneous space on the two copies of H. So in this case, we take the subgroup K to be just H itself. It's embedded diagonally into G. So let me try if I can write on this slide. So here, just take H. Okay, this works. This is, I just consider the diagonal embedding. So in their work, they use the following fact due to Ginzburg. So Ginzburg shows that Harish-Chandra GK modules, in this case, they are something better known as Harish-Chandra bimodules. This is just terminology. They showed that Harish-Chandra bimodules localized to regular holonomic B modules over H. We have this nice theorem. Ginzburg. So a natural question is to ask, what about more general homogeneous spaces other than H itself? So the next case beyond the group case is algebraic symmetric spaces. This means we consider This means we consider we consider something like X equals G mod H, where H it is sandwiched between a fixed point of some involution theta and its connected component. Theta is involution on G. This is what we mean by algebraic symmetric space. And even larger families, so-called spherical varieties. So this means there is an open Borel orbit on X. So so yeah. Okay, so I said it's important to look at the derived functor of the localization. So let me explain this problem. So let's G be a can you hear me? If the connection dropped, please tell me. Okay.
Yeah, we can hear. Yeah.
Okay, thank you. So how about derived functors? So let's assume X to be a homogeneous affine space under G. So affine is equivalent to that H is reductive. So we take the left derived functor of this guy, and we take the derived tensor product. So here is some proposition exercise. It shows that, okay, if you take localization and take a fiber at X and take homologies, then we just get the Lie algebra homology of V taken over H, Lie algebra H. And its dual is the extension group of V, still taken over H. And here Ix is the derived version of the inverse image functor. So it sends a dx module, or a complex of dx module, to a complex of d modules over a point. But d modules over a point is nothing but just a C module, so C vector space. So this functor goes into the derived functor of C. So I said the study of spaces like home H VC is somehow related to what I called branching laws. So if you replace home by X, then we get something higher. It suggests some link between localizations and higher branching laws. Yeah, so this is the topic of my talk today. So actually, this is proposed by Dipendra Prasad in a previous ICN talk. So let me take connected reductive group G and subgroup H. So in the periodic case, the higher branching laws studies extension like before, extension V, C taken over H. V is a so-called admissible representation of GQP. So you can also replace C by some more general representations of H, but there's some standard recipe to reduce to the previous case. You just embed H into a G times H diagonally. So in this way, you can reduce to a case where W is C. And we are also interested in Euler-Poincare characteristic. But we should show it is well defined. So for example, we want this dimension to be finite. And we also want this sum over n is also finite. If everything is finite, then this Euler-Poincare characteristic is well defined. So this is about periodic groups. But what about real groups? So, okay, so stated like this. So we want to study the same extension groups, but here V is taken from some category. And we take X over some category. It's associated with H. So the problem is how to choose these categories. So the first question is try to formulate it by choosing some suitable categories. And secondly, try to relate it to localization as before. And the third question is about something about finiteness. We want to well define these Euler-Poincare characteristics. Okay, any questions? There's no question. Let me formulate. So, okay. So actually, there are more than one choice. Is more than one choice. So, but today, I will focus on the algebraic setting. So there is an algebraic choice of these categories. So we consider G to be a connected reductive complex group. We take 4 subgroups. One is H, another one is K, and then we also take some KH. Lies in both subgroups. So we study a functor from a GK module to HKH module. But I still denote it as a restriction as this, and we shall study the extension groups accordingly. If you take KH to be the trivial groups, then we fall back to the extension groups over the algebras mentioned before. And in that case, we see it is related to higher localization. But we also want to allow a more general KH. So this will be addressed later on. And I should say, this is just the algebraic formulation. There are also analytic formulations, because Lie groups is really a topic about analysis. We can also formulate same question using facial representations and take continuous Hom instead of linear Hom. Let's more complicated. I will return to this issue later on. Yes. So okay. So this is algebraic formulation, but we said we want to relate this to localization. So here the difference is, okay, we consider not just G modules, but also GK modules. So let me repeat that we fix two subgroups K and H of G, and we take the affine homogeneous space G mod H, and also the standard base point. And we should consider dx K modules. So this is just the same as K equivariant D modules on X. And our goal is to take the derived functor as before of this localization functor as before. But here I add an equivariance under K on both sides. We want to left derive this functor and try to relate it to branching laws or higher branching laws. But if you try to take the right functors in the usual way, it won't work. This is somehow delicate question about definitions. It's also a question about categories. So it's a problem of type mismatch. Why? Because so I said there's also a question about cats. So I draw a cat here. So first, on the left-hand side, we want to take the right category of this guy. So okay, there's a standard choice. Just take the right category in the usual way. Reference is the textbook of Knapp and Logan. But on the right-hand side, we can also, if you take the usual derived category of this abelian category, then people know it. The result is not what you really want. So the correct way is to take the bounded equivariant derived category of D modules. So the standard version is due to Bernstein lumps. So this requires some resolutions of X. So this means that we want to replace X by some larger G variety P. So that's a G equivariant map from P to X. But condition is that if we take the condition is that G must act freely on P. So sorry. So we want to resolve X by some variety with free G action, and also we want this guy to have somehow highly connected fibers. This is how Bernstein and Luntz solve this problem. But I know of no obvious definition to define the right functor using resolutions in this way, because first problem is localization doesn't behave so well on the equivariant maps. If you have so I don't know how to prescribe a compatible family of D modules on these resolutions. And secondly, even if you can do it in this way, it is hard to use because I really want to work on X and not on resolution P. Going to P will lose too much information. So maybe a more recent here there is we now have a theory of D modules on stacks, but this doesn't help too much for the same reasons, because we want to avoid using resolutions. So I don't think infinite categories or derived geometry is it. I don't think they help here. Anyway. Okay, but anyway, if it makes some sense to take derived functor, then we hope that it will commute with forgetful functor. Here I call it oblivion. And I also hope it to be related to higher branching laws. And finally, we want to say something about the image of Harish-Chandra modules. For example, if we localize the Harish-Chandra GK module, do we get something with regular holonomic cohomologies? Of course, this requires some conditions on H and K. Here, I think the condition is about sphericity mentioned above. Here we say a subgroup H is spherical if the homogeneous space is a spherical variety. So my proposal to this problem is to take something called h-derived categories and take h-derived functors. I think this is due to Beilinson-Ginzburg in some Russian paper. It's written down in English in some later paper by Bernstein and Nuts. And this will give you some localization functor like this. And the H, they didn't say what H means, but I think H means homotopy. Homotopy complexes. Okay, so let me explain their ideas. So first, let's A is an algebra, so it is either UG or DX. In either case, we have an algebraic action by K, in fact by G, and we also have some homomorphism from K into A. So if A is UG, this is just the inclusion. If A is DX, this is given by infinitesimal action. So by a weak AK module, I mean a left A module with an algebraic K action, but I want them to be compatible in this sense. So compatible in this sense. And we say it is an AK module if I require that the derivative of the K action is the same as the action obtained by J. We embed K into A and then we let A act on N. And I want this to be just 0. So this unifies the notion of GK modules and the K equivariant D modules on X. And of course, this definition is quite general. You can take some other A, some algebra A with an algebraic K action. So the result is called Harish-Chandra algebras. All these are in the paper of Bernstein and Nuts. Okay. Any questions? Okay, so I will go on. So an H complex, remember H means homotopy. So it is a complex of weak AK modules. Not AK modules, I only require weak AK modules, but it's something else. We are also given a family of maps IC. They are degree -1 endomorphisms of this complex. They are linear in C. So that there are lots of compatibilities here, but I think the outstanding condition is this one. So we take the DI plus ID, and I want it to be exactly the obstruction for the complex to be a complex of strong modules instead of weak modules. of course, they are just weak modules, but I prescribe the homotopy from this obstruction to 0. This is the idea. So in particular, if you have a complex of AK modules, you have an H complex by setting XC to be 0. And secondly, if we take a cohomologies of the H complex, then the homotopy here tell you that the cohomologies are AK modules, not just weak AK modules. This is the main idea. Okay, so in this setting, there are reasonable definitions of Hom complexes, mapping combs, translation functors, and so on for H complexes. So we can define the homotopy category, the derived categories in this way. And you can also impose boundedness conditions. It's also triangulated with a T structure. So we can define R Hom and the extension, and its heart is exactly the abelian category of AK modules. And finally, one can also define derived functors. Here I call it h-derived functors. So this just follows from the abstract definition of derived functors in terms of universal properties. In fact, it is defined as some COM extensions. And it is computed by taking not just projective or injective resolution, but something called K-projective and K-injective resolutions. All these notions are more or less well known in homological algebra. But if you try to check all these conditions by hand, things will get more and more complicated and unmotivated. So the conceptual way to organize all this framework is to consider DG modules over DG algebra. Here, DG algebra is UK bar tensor A. Here, UK bar is something defined in this way. This is a DG algebra. And maybe a more conceptual way is to understand this as the universal enveloping algebra of a DG algebra. We have two copies of K. This is identity map. This is degree -1. This is in degree 1. So this is something called a DG algebra. Take its universal enveloping DG algebra, we get this one. And moreover, there's also a K here. So we want to impose K equivariance somehow. But if you work in the DG context, everything is naturally defined. There is no ad hoc constructions anymore. Okay, any questions? If not, I will proceed. So once the formalism is set up, and this is not too hard if you know how to do it, it's easy to lift the localization to H level, and we take the left h-derived functors. So now higher localization looks like this. It is something between the h-derived categories, and here I work with the bounded version. You can show that it preserves bounded complexes, and you can also show that everything is compatible with forgetful functors. And I said this before, you can bound its amplitude easily. Yes, so localization commutes with forgetful functors, and also cohomologies commutes with forgetful functors. Everything, this is quite routine fact to check. So yes, it's a routine. So it is now a routine to relate the fibers of higher localizations to higher branching. So this is just the derived version of the of an exercise that I mentioned earlier. So if you take the derived localization, you take the derived inverse image, you land in the equivariant derived category over a point. Here, equivariance comes from KH. It is a subgroup of H. And this gives you the extension group. And the same for the relative algebra homologies. Here, I take the derived localization followed by fiber. Take the co-invariant somehow. Co-invariant is an operation that gets rid of the KH equivariance. And then we take the homologies. So, but here, extension group is taken in the h-derived categories, not the usual derived categories. And here V is any GK module, IX is the derived inverse image of equivariant D modules. There's a co-invariant somehow here. So, so to get back to our original problem, we have to relate this extension group to the familiar extension group. And we also want to get back to the familiar equivariant derived category of D modules. This is possible. In fact, Beilinson and Lumt and later Pensich showed that the H-derived category over GK is just the usual one, the same for the bounded version. And same for the D modules. So for any smooth G variety X, not just affine, they consider a general case. The bounded derived category is the H it is equal to its H version. And it is also compatible with the inverse image functors. So we have now come full circle. So the H-derived categories give the same extension groups, and the localization functor can be identified as a boundary between the familiar derived categories. But we still have a question. We want to say something about the image of this derived functor. For example, regularity and so on. So okay, so here's a theorem. So let H and K be reductive groups, and we take X to be affine homogeneous space G mod H, and now we assume that H and K are spherical, and V is a Harish-Chandra GK module. Then the cohomologies of the higher localization are for regular holonomic. In fact, we can also control its characteristic variety. It is in the pre-image of nilpotent cone under the moment map. The proof is based on a criterion, one of my earlier paper. And in turn, it is a variant of Ginzburg's results in case H equals K, both are symmetric subgroups of G. Let me sketch the proof because it is really elementary modulo this criteria. So the sketch of the regularity is follows. So let's take the higher localization, but without any equivariant conditions. So by the papers cited above, we just have to show three conditions R1 to R3. R1 says each cohomology of L is finite generated as a D module. R2 says it comes with a K equivariant structure, and the R3 says it is locally ZG finite if we let ZG act through DX in this way. So maybe you can already observe that this really look like the definition of Harish-Chandra GK modules. Sorry, we just replace all the condition about the algebras by conditions about D modules. So once these three conditions holds, we can show its regularity, since we assume H and K are spherical. So R1 is easy. It's essentially based on finite generation of V and some Noetherian properties of these algebras. R2 is also immediate because Hn of L, it comes from something with K equivariance. And R3, local GG finiteness, is the technical part. And it reduces to the following lemma. The lemma says, if X is a smooth affine G variety, V is a finite generated local GG finite G module, then the higher Tor groups of this D and V, they are locally GG finite. Okay, so let's sketch a proof of this lemma. I will go quickly. So first, let's consider the algebra of G invariant differential operators on X, but furthermore, I take its center. If X is spherical, then this is just the whole algebra of invariant differential operators. So by induction, to prove this Tor is locally GG finite, it suffices to take a V equals a UG modulo kernel of chi times UG, where chi is an infinitesimal character. And secondly, we can reduce to the local GG finiteness of this guy. Why? Because by definition, M chi is tensor product from N chi, where N chi is just GG modulo kernel chi. But we have this diagram here. This is the key diagram. So UG is actually a free over ZG. This is a theorem of constant. So you can put an L in this tensor product. But now we go the other way around through this diagram. So we now go from ZG to ZX, and then go from ZX to DX. And the second step is again free. This is a deep theorem of Knoop. Okay, in fact, both theorems are quite deep, I think. So we finally get this thing. So the Tor only occurred in the second tensor slot. We want to say this guy is locally GG finite. And this simplifies our problem because ZX is now a commutative algebra. And it's now relatively easy to show that this Tor guy is GG finite. In fact, ZGX via chi. So now we take, remember that we want to show this guy to be a locally GG finite. So, but we know this guy is generated over dx by this guy. And I make it slightly bigger by acting by UG. So this gives something called M nature. It's now a G sub module. And we know that this green guy is GG finite. So this guy generated by M flat is also locally GG finite. So now we have G linear surjection here, just given in an obvious way. This is G linear if we let GX on DX by conjugation. not by left multiplication, but by conjugation, or the derivative of the conjugation. So to get a GG linear surjection like this. So the problem is reduced to show this guy is also a GG locally finite. But finally, a DX is a union of finite dimensional G modules. So we are actually taking a tensor product with a finite G representation with something locally G finite. And this is also a locally G finite stuff. So again, this is a non-trivial theorem due to constant. So lemma is proved in this way. So this is probably somehow roundabout, but the idea is quite simple. So everything is simple modulo Knoop and constant. So actually, a Knoop given quite explicit description of this ring GX, and the ring also offers some symmetries on this localization functor. In this way, you can spread this localization functor over the spectrum of GX. And also, I expect some applications beyond branching lobes, for example, in geometric representation theory. I don't know if there's any such application, but I hope so. So what is regularity good for? Okay, so the Theorem 2 is something like this. So the extension groups in question is isomorphic to extension group of localization followed by IX strict, followed with some shift. This is essentially a restatement of an earlier isomorphism. And we also have some dual version for the algebra homologies. Here, I strict is defined to match the I strict for constructible shifts on the Riemann-Hilbert correspondence. But once you write things like in this way, you see that every D module is regular holonomic. And you take all these extensions and so on. We always land in some category with finiteness conditions. So in fact, we can show in this way all these spaces are finite dimension. We have the finiteness property. And we also get some a little bit geometric interpretations of these extension groups, but maybe not so geometric because anyway, it implies finiteness. So, but recently I found Kitagawa. He obtained stronger results on finiteness in a recent preprint. He also used localization, but it's Bernstein-Beilinson localization. He also used Zuckerman functors. And he proceeds in a completely different way. He considered the algebra cohomologies, and then he passed to homologies using Poincare duality. And if you take KH trivial, then finiteness also known earlier under some mild assumptions by Eisenberg, Gurevich, Klotz, and Liu Gang. And in this case, you can state these results without H complexes. But to prove regularity, we still need to use H complexes in some secret way. I cannot make it disappear completely. So, okay, so anyway, under these assumptions, the Euler-Poincare characteristic is defined because the sum of n is finite. I have bounded the amplitude here. And also each extension group is also finite dimension. So this Euler-Poincare is well defined. And in the simple case, H trivial is poised and interesting topological stuff. So Theorem says if you take L to be the localization of V, then the Euler-Poincare characteristic of V and C equals the local Euler-Poincare characteristic of the something in D-module theory called the solution complex of L. Solution complex. And this can be expressed in terms of characteristic cycles and some topological stuff called Euler obstructions using Kashiwara's local index theorem. Is written there, written below. But I wrote some approximation here because maybe there will be some plus or minus sign here. I'm not sure. Anyway, so far I don't know any explicit description of this characteristic cycle. So this is only an abstract result so far. And I will pass through this slide. So I will pass quickly. So in applications, we also like to consider extension groups like this. So we replace C by some one-dimensional character chi. So this can also fit into a geometric picture. So we want to replace X by some tensor over X. And the corresponding differential operators on X must be twisted accordingly using X tilde and the character chi. Okay, I won't go into the details, but anyway, if you twist everything, then all the previous results will carry over, except that's about solution complexes, because I don't know about any twisted version of local index theorem. But in practice, people also like to have finite dimensional modules instead of one-dimensional modules. But my method cannot cover this case. But in the periodic case, we only have one-dimensional chi. So the version above algebraic formulation of branching, but there is also an analytic formulation. So I will sketch this theory. So in this case, we take G and H to be connected real algebraic groups. And the representations in question are really representation, but they are smooth and the Fresher representations. Smooth means every vector is differentiable under the G action. Fresher means the underlying space is Fresher space. Of moderate growth means something that I cannot explain here, but almost everything you can write down is of moderate growth. And the Hom space is, of course, continuous Hom. So define EH to be the algebraic co-invariance on the H that's endowed with the quotient topology. So this can, a priori, this can be non-Hausdorff. Then the invariant linear functionals are just the continuous deal of EH. So this formalism is probably more realistic for real applications in harmonic analysis. So how about the higher version? So if we want to define extension groups, then I think there are some problems, but we can go directly to the Lie algebra homologies, Lie group homologies somehow. And in fact, Chen Yang and Shen Bingyong recently they construct a theory called Schwarz homologies. It's seemed to fit well with the applications. These are a sequence of locally convex topological vector spaces. Again, are not always Hausdorff. In degree 0, it is just co-invariant. So homological branching law in this setting amounts to studying these homologies for Kasselman-Wallach representation E of G. you can imagine that the Kasselman-Walla representation is just some counterpart of the Harish-Chandra GK modules. So in this case, we take let's take small h and small g be the complex the algebra. So this is somehow related to Harish-Chandra GK modules. Okay, okay, we take a maximal compact subgroup K, so that K cap H is a maximal compact in H. Then Chen and Shen prove that their homologies are the same as relatively algebra homologies. The left-hand side is defined using a usual complex, but I don't assume E is an HKH module in the algebraic sense. Just drop all the algebraic assumptions in definition. So this can be compared with algebraic formalism. So we get a comparison map from the algebraic version to the Schwarz version. Here, V is the subspace of K finite vectors in our Fresher representation, E. And this is a Harish-Chandra GK module. So the natural question is, okay, let's put the usual assumptions, reductive and spherical and so on, and ask when is Qian isomorphism? I don't dare to call it a conjecture because the consequences are probably too strong to hold in general. For example, if this is always an isomorphism, then dimension of these Schwarz homologies will be finite. And it's also well known that finiteness will imply Hausdorffness in this setting. And in the case n equals 0, it will imply some strong result called automatic continuity. So far, this is only known for symmetric subgroups or maximal unipotent subgroups if you go beyond reductive subgroups. So this is too strong, but I managed to show that it holds in some cases. For example, if you assume EH to be admissible over KH, this is a condition studied by Toshiyuki Kobayashi long time ago in the analytic setting. Then the comparison map is always an isomorphism. This is a rare phenomenon that includes already some interesting cases. For example, the case of homomorphic discrete series of emission big groups. For example, representations of SL2R corresponding to holomorphic modular forms, and so on. The second case is if you take G to be SL2, this is everyone's favorite example, and then there are not too many candidates of H. Let's take H to be a diagonal subgroup K SL2. K is SL2, sorry. Then the comparison map is always isomorphism. So step one is to reduce to principal series by a general argument due to Haidt and Taylor. And second step is to compute directly with principal series to show that we get an isomorphism between homologies. This is not that hard because there are only 2 degrees of homologies to check. And it shows it does happen that H1 can be non-zero. So we are not working on something that's always trivial. In this case, H is always a symmetric group. This falls under a symmetric case. Still not trivial. So much of this work is about the choice of good category and then reduced to no results of Knoop constant. So let me stop here, and I wish also mention that details can be found in recent archive. In fact, it just appeared a few hours ago on archive. Thank you.
Yes, thanks for the talk. Yes. Okay, so any question for the speaker and also for the talk?
Professor, could you hear me?
Yes, please. Yes.
Is there any relation between the work you talked today with the joint work of Sun Bingyuan and Huang Jinsong? Is there joint work on custom analytic conjecture?
Sorry, can you say again?
Is there
They
any
work on what?
Is there any relation with your today's work with the custom orthogonality conjecture done by Sun and Huang?
Okay, I have to say that I don't really know very much about their work. I heard about it, but I don't know details. But I think what they study is about, I will write here on my slides. So I think they are studying something of extensions of GK modules between two GK modules, VWR, probably Harish-Chandra GK modules. And I think they are considering the Euler-Poincare characteristic, and is equals something. So is this what you mean?
Yes.
I don't know. I hope. Okay, so in my work, I showed this is something related to D modules, and I hope that you can also go directly from D modules to their formula, but sorry that the results interpretation in terms of D modules, I don't know how to use it in concrete cases. So this I must put some question marks here. I don't know how to go directly between these two words. In fact, I think in any case, in case that if you have any way to deal with extension groups directly, then it's always easier than going through D modules. So going through D modules somehow, it often makes the problem more complicated somehow. So my answer is I don't know. Sorry.
Okay.
Okay. Okay, yeah, there is a question in the chat here.
Yes, okay.
Yeah.
So Hu Xiaowen is, are the cohomologies expected to be regular holonomic? I don't think so, but in my talk, I assume H and K to be spherical. So for non-spherical case and for non-spherical case, I think even in degree 0, one can produce irregular D modules, or even maybe it is even easy to produce non-holonomic D modules without spherical condition. I don't have any concrete example at hand, but I think there exist some common examples. Yes, so it's a spherical condition. I think it's a crucial ingredient here. Yes, even in degree 0.
Okay.
Hi.
Hi.
Do you expect some algebraic structure like the Cartan-Ludwig Bogen module in your work?
I'm not sure what this means, but I don't think so. No, maybe you mean so in the case of KLV polynomials, it is also related to computing some extension groups. But I don't. But in the case I consider here, so far I don't see any connection with such polynomials or any such geometric structures. I don't know.
Yeah. Thank you.
Thank you.
Okay. So any more questions about the talk? Okay, yeah, probably let's thank the speaker. Yeah.
Okay, thank you. Thank you.
Yeah.